Hey guys, Mr. Pauller here. In this video, I'll be showing two calculations using Snell's law. Let's start by talking about refraction. This phenomenon happens when light travels from a medium like air into a new medium like water. You can see the plastic pipette in the image appears bent. This is not because the pipette is actually bending, but rather because the light is bending. The changing path of light creates an optical illusion that the pipette is bent. Other examples of refraction include prisms, rainbows, and that cool trick with the arrow that changes direction that you may have seen on YouTube. We can use Snell's law to calculate information about light waves that are being refracted. Let's take a look at an online simulation from PhET called Bending Light to collect some data for calculations. In order to collect our data, we need to define some variables. Theta 1 is the incident angle of the light and is measured in degrees off from the perpendicular, which is called normal. Theta 2 is the angle of refraction, which shows the altered path of the light. We also need the refractive index for each medium. Those are listed as N1 and N2. The index of refraction can be used to describe how fast light will move through a material. Let's use the PhET sim to collect some data. I'm going to set it up so that we have water in the top and mystery material A in the bottom. I'll turn on the laser and set the incident angle to 55 degrees. You can see that the angle of refraction is 28 degrees. We can use these measurements, plus the index of refraction for water, to calculate the index of refraction for the unknown material. There's a great physics website called Hyperphysics that has a Snell's law calculator. I'll include a link to the site in the video description. To do the calculation, we just need to enter the known variables. N1 equals 1.33, Theta 1 equals 55, Theta 2 equals 28, and N2 is the unknown. To complete the calculation, you click on the N2 in the equation, and then it will display the answer. N2 equals 2.3206. Now let's solve this one without hyperphysics. I'll start by identifying the variables. Instead of using N1, I'm going to use NW since it gives us the index of refraction for water. I'll use NA instead of N2 for mystery material A. We will use theta W for the incident angle since this angle is in the water, and theta A for the angle of refraction because this angle is in material A. I'll write the equation for Snell's law first. NW sine theta W equals NA sine theta A. Because we want to solve for NA, I'll divide each side by sine theta A. This tells us that NA equals NW sine theta W divided by sine theta A. By plugging in the known variables, the equation becomes 1.33 times sine of 55 divided by the sine of 28. To calculate the answer, I'm going to use the Google calculator. Whichever calculator you use, make sure you set it to degrees. I'm going to work my way out in this calculation. So first you want to find the sine of 55. Close the parentheses and we get 0.819. If you got negative 0.9997, you are in radians. Clear that, select degree, and start over. Okay, we have the sine of 55. Now multiply by 1.33 and then finally divide by the sine of 28. We get an answer of 2.3206, which matches the result we got using the Hyperphysics Snell's law calculator. The final answer should be rounded to 3 significant figures, so report a final answer of 2.32. A common application of this in lab would be to identify an unknown sample by experimentally determining its index of refraction and comparing the result to a table of index of refraction values for common substances. It looks like our result is slightly off due to uncertainty in the measurements, but mystery material A appears to be a diamond. Now let's look at an example making a prediction for an angle of refraction. In this problem, we have light traveling through air and entering into water with an incident angle of 63.5 degrees. The N1 for air is 1.00 and the N2 for water is 1.33. To solve, we will begin by writing out Snell's law. I will use W for water and A for air. NW sine theta W equals NA sine theta A. Now I'll divide each side by NW, and then I will take the inverse sine for each side. This allows us to solve the equation for the unknown. Theta W equals inverse sine NA sine theta A divided by NW. Now we want to plug in our known values, and that gives theta W equals sine to the minus 1, 1.00 times sine of 63.5 degrees divided by 1.33. To use the Google calculator, make sure you are in degrees and start the calculation by finding the sine of 63.5. You should get 0.8949. If you don't, check to make sure your calculator is in degrees, not radians. Next, multiply by 1 and then divide by 1.33. Now click on AC. The value you just calculated will be stored in the memory of the calculator. After clearing, click Inverse, then Sine, and you will see the calculator display arc sine. Click on ANS in the bottom left corner to get back your previous calculation. Next, close the parentheses and then click on the equal sign. After rounding for sig figs, the answer is 42.3. Let's enter these values into the hyperphysics calculator to check our work. N1 equals 1.00, N2 equals 1.33, theta 1 equals 63.5 degrees, and theta 2 is the unknown. Clicking on theta 2 in the equation gives the result of 42.3 degrees for the angle of refraction, just like we calculated. Now we can use the PhET simulation to check this result. By setting the top medium to air, the bottom medium to water, and the incident angle to 63.5, we can see that the angle of refraction matches our calculation. Thank you for watching. I hope you found this video helpful. If you have any questions about Snell's law, refraction, or just want to leave me a note, you can use the comment section below. And until next time, stay curious.